You can start, Sita.
Hi all once again to the Pi Seminar series and dedicated towards advancements in scientific machine learning. Today we have with us Jassem Abbasi, who's a PhD candidate in the Department of Energy Resources at the University of Stavanger, Norway. His research leverages machine learning to enhance the characterization of complex processes of multi-phase flow in porous media. Jason brings nearly 4 years of experience as a reservoir simulation engineer and scientific software developer. With a background in reservoir engineering, his technical expertise includes geoscience, subsurface fluid flow, simulation, field development planning, and thermodynamic modeling of fluid properties. So today's talk is going to be on history matching of imbibition flows in multi-scale fractured porous media using physics-informed neural networks. So over to you, Jason, for rest of the talk.
Yeah, thank you so much, and thank you so much for having me here. It's my pleasure to present here, and yeah, let's see. So now I'm going to share my screen. Okay, so you should see the PowerPoint at the moment. Am I right?
Yes, we can see.
Yes. Okay. So I think I should change the screen. So you're seeing the presentation or the task bar
We
and
do,
things like
we do
that.
see the presentation. Together with that, we also get to see the next slide of yours. So I think,
Okay, so I should
yeah,
probably change the screen.
yes.
Mm, let me. mm, No, I think you're still seeing.
Yes, now it's
Yeah,
good. Yeah,
that's good.
yeah, it's good. It's good.
Yeah, okay. Yes, so thank you so much again for inviting me, and it's my pleasure to present our last work about history matching of flow in multi-scale fracture cross media using physics-informed neural networks as an alternative method for like traditional numerical methods that we use in the in this field of science and engineering. Uh, this work have been done with collaboration with like here at University of Stavanger at ETH Zurich and with Ameya before at Brown University and now at Worcester Polytechnic University and Stanford University. With like we used like experimental data with pins-based methods, and we are going to see the results at the moment. So we'll first have an introduction to the problem, then we will introduce the methodology, then we'll see what problem we have studied and the characteristics of flowing fracture cross media, and then we will see some parts of the results of our work. First, the fractured cross media. So almost all natural cross media that we see, like in the nature, like subsurface geological formations, we can say that are to some degree fractured in a way. But because of limitations in computational resources and computational limitations that we have, we normally overlook those fractures and the impact of fractures in the systems that is not easy to overlook in many cases. So we need some newer computational resources or computational methods to reevaluate all the calculations or the methodologies that we had before and come up with much more advanced evaluations that can help us to reach to better evaluations in the properties of the porous media, both in the matrix or the rock and the fractures. It helps us in many applications in like efficient production of oil and gas, for example, or storage of carbon in subsurface, or storage of hydrogen in subsurface, or like management of water resources in subsurface. That is very important in many industries and many scientific fields. In this work, as I mentioned, we are going to develop a new computational tool based on physics-informed neural networks for history matching of experimental evaluations that we normally do in like natural porous media or rocks that we have from subsurface fields. And we will see that how it helps in improving the current practices in management of or characterization of flow in porous media, fractured porous media. So, like here, the case that we are going to study is a case of two-phase flow in fractured porous media, and the fluids are water and CO2. So the rock is, we have a cylindrical rock that is like this here, and we inject from one side and produce from the other side. The rock is firstly saturated by CO2, so it's the pore spaces or pore volume is fully saturated by CO2. Then we inject water, and the rock is a shale rock that like is famous for its very low permeability and very tight properties, very low porosity, so very low fraction of void spaces in a way. And it's like this is like a picture of a shale rock. And the shale rocks, because they are very kind of stiff, they can be easily fractured, and you see them in nature that they are fractured, as you can see in the picture. In this case, also the rock that we had, or the core plug that we had, was fractured, and we, using this micro CT scan imaging, we could extract the properties of the fractures, and you can see this is the fractures in this core plug, in this cylindrical core plug, and it's heavily distributed irregularly in the rock. And this is like a symbolic schematic of how like we have flow when we are injecting water. And you can see that the water bypasses through the matrix through the fracture, and the most of the flow passes through the fractures, not the matrix. But it's very important for us to characterize both properties of matrix, that is the rock itself or the shale rock, and the fractures. That is not easily possible using traditional methods. That's the point of this study in a way. So here, kind of the goal is extracting the properties of rock and the fractures by having a look at the experimental data that we have, or performing some inverse calculations. So the properties that have been calculated at this stage would be then upscaled by like engineers or reservoir engineers and petroleum engineers or like geoscientists to the higher scales of magnitude, and it would be like applied to field scale, or like with kilometers of like dimensions in each dimension, and like it would be used for prediction of like flow of fluids in subsurface reservoirs, like how fluids flow in like oil and gas reservoirs. and how we can optimize that process and improve the process, the petroleum or like gas productions from those reservoirs that can the properties that calculated can make millions of dollars of change in the the eventual economics of the projects. So it's very important to characterize these properties very well, and that is normally not very possible because of the limitations in the measurements, in experimental setups, and in computational resources that we have. But now we are going to see how we can fix this issue. As I mentioned before, this is an example of how this is important to have the knowledge, good knowledge about the properties of the porous media that we have in nature. So here is an example of injecting CO2 in subsurface reservoirs for the reason of carbon storage or carbon capturing. And so the properties that we are going to calculate can change how the fluids migrate in the subsurface, and the volume of the CO2 that we can inject to have secure storage and without having any leakage to the nature, to the surface of the the area that we are going to inject. So we can say that this is one of the most important parameters that is going to be used for large scale processes. About the mathematical system or the PDEs that we are going to solve here. So we have a complex system in a way. So we have two mediums in a way, one for matrix and one for fracture system. Each one is behaving differently in a way. Matrix generally have a very low permeability, meaning that the fluids can pass very slowly in the porous media. But fractures have very, very high permeability, meaning that fluids can pass easily and quickly break through to the other sides of the the domain that we have. But they have interactions with each other. Matrix and fracture having fluid transfer and pressure transfer with each other that needs to be considered during the evaluation. So they are not decoupled in a way. They are very coupled, and but they are showing very different properties at the same time, in a way, multi-scale flow properties in a way. At each domain, we need to solve these properties for each fluid that we have. Here, the problem is two-phase, CO2 and water. So we should solve this PDE, that is a conservation law PDE, a hyperbolic PDE for both wetting and non-wetting phase, or water and CO2, we call it. And same should be solved for fractures. And we have a transfer term Q that determines the transfer between matrix and fracture at the intersection between matrix and fracture. At the other areas that matrix and fracture don't have any interaction, so this Q would be 0. But in the intersections, this should be considered. The velocity of fluid is determined by Darcy law, that is a factor of some natural properties of the rock, that we call it relative permeability or absolute permeability, and the viscosity of fluids. And of course, the matrix transfer mass transfer is determined by the pressure of two mediums, matrix and fracture, and some properties of matrix and fracture. That all of these equations should be solved at the same time. And in this problem, because the fractures are behaving distributed in a 3D way, so the flow in porous media and in fractures also kind of 3D. So we need to solve this problem, these PDEs, in 3 dimensions, not 1 or 2. That makes the computations even much more difficult. The parameters that we are looking for in inverse problems or in inverse calculations are the property or the flow properties of matrix and fracture. that is not possible to be calculated in other ways. So it's a flow property. So the experiment should have some flow to measure it. And this is the experiment that we have in the laboratory to measure these properties. The properties that we are going to calculate, I highlighted them, is some properties of like the maximum relative permeability for each phase, and some exponent that's showing the shape of these curves. And the curves are themselves a function of saturation of water. And so the shape of this curve is very important for us in like reservoir simulations and in larger scale prediction of flow in porous media. And of course, we need to calculate the capillary pressure curves, that is like determining the speed of imbibition in rock in a very low radius pores. And this one is also, this curve is also calculated by like a correlation that we use, and the unknown variables are J1 and J2. So it's like a kind of simple equation in a way, but it's still not very easy to calculate. This equation gives us this curve, this capillary pressure curve, that is kind of very important for us in showing how fluids are flowing in different spaces in a way, in matrix and fracture. Although we don't have any knowledge about, we have knowledge, we have measured average permeability of the core, but we didn't have any information about the permeability of each domain, matrix and fracture. We knew that they have very different permeability values, orders of magnitude, but we didn't have any information about it. We made some assumptions here that is like normal in this field, that like relative permeabilities in fractures are like linear, so it makes us able to use Darcy law for it for this purpose. And that we don't have any capillary pressure in fractures. That's also like a simplified assumption that is kind of normal in this domain. Then we started to calculate, but we also wanted to calculate the permeability of the fracture, because permeability, absolute permeability, was important for us to characterize the properties of the fracture at the same time with the matrix.
Just
So
can I, so the NW1 and NW2, are they do they have any physical meaning, or are they just weights for this equation that you're trying to solve?
They have some physical meanings,
Okay.
like that is kind of known in petroleum engineering, reservoir engineering. So this NW1 and 2 and in of non-wet, they are determining the shape of these curves.
Okay.
And the shape of
And SW is your volume fraction, or is it right to say it is a volume fraction of gas and water, or is it?
Yes, exactly. So
okay.
SW means the volume fraction of like wetting phase or water here.
Right.
So it's a function. So the NW value is a function of this volume fraction of each phase in a way. And the shape of this curve determines how like each fluid is flowing with respect to each other one. So like if at this saturation, we can see that gas is flowing much quicker than like water. But at this saturation, we can see that relatively water is flowing much quicker than gas. So this shape determines that which phase like will reach to the production well or to the other side of the domain more easily. So in general scale, in larger scale simulations, this curve like can tune how each fluid is flowing and how the fluids are distributed in the whole field that we have in scales of kilometers in a way. So this curve is very important for us in like reservoir engineering, in geoscience. So yes,
sorry to interrupt, Jassem. There is another question on the chat box. That's raised by Trishit.
Trishit, you can ask your question. You can unmute yourself and ask your question.
Okay, so I was asking if the critical saturation is known or not. Like in these unknown properties, critical saturation is also unknown.
Yeah, critical saturation here, like we assume that at first, like we had information, we had CT scan images, we had information that how much the like the rack or the core is saturated by CO2. So we had information about the initial saturation. And of course, we had information about the final saturation because we continued the experiment like for a while and it stopped the production. So we assume these curves as like those points as the critical saturations in a way, or irreducible saturations for two phases.
Yeah, okay, correct.
Yes. Thank you. Yeah. So then I will introduce physics-informed neural networks that I think is not very necessary here in this community. So physics-informed neural network first introduced by Ray C. et al. At 2019, formally published, and it's a combination of using machine learning, physics, and the numerical methods for performing scientific calculations using performing optimization and the loss function, the composite loss function that we define based on the like the PD and the data that we have and the boundary conditions. So we think in the engineering problems that we have in like Porous media, we think it has some advantages that should be considered. Of course, it can be used for forward simulation, for history matching, uncertainty quantification, and data-driven modeling. But the advantages that we think should be taught is like it's reliable for mixed data types. When we have like multi-fidelity data types, that is not like cannot be easily applied for using like numerical methods. It's very flexible for noisy or incomplete data that also is a challenge for other methods. It's very good for inverse calculations or history matching, and maybe more reliable for sensitivity analysis on parameters. And we hope that it's can like perform interpretations on live experimental data or live data with very low supervision. Of course, it needs some more developments to reach this point, but still there is a potential. So here we had a very complex complex problem, and complex system of equations. So we needed some specialized architecture in general to reach to the solution. So this is like some snapshots of the core that we had, and it shows that how fracture distributed in the core. Here we extracted using like the CT scan images that we had. We extracted the collocation points from both matrix and fracture that you can see. And then, so this was like our collocation points. And about the network architecture, here we used, so we decoupled matrix and fractured, and then we defined some coupled interaction between those domains to connect, to connect those domains to each other. So here we had the two networks for matrix and two networks for fracture. And so for each domain, we had two networks, each one representing the state variable of the system. That was the saturation of water, that is like volume fraction of fluid at each point, and the pressure of each phase, that is like pressure of non-wetting phase here, or pressure of CO2. So then we could calculate the pressure of wetting phase using the calculated properties. We also had same system for fracture, water saturation in the fracture, and pressure in the fracture. For each domain, for each network, we had like a deep learning architecture that had an encoder, a Fourier transformer, a latent network with an activation function, adaptive activation function, and an inverse Fourier transformer, and then a decoder, and like with normalization and denormalization calculations. Yeah, but for pressure, we haven't used like Fourier transformation because it was showing less kind of frequencies in the system. So we thought it's not needed to use like Fourier operator, because Fourier operator here was helping us to like kind of manage the high frequencies in the distribution of saturation, the 3 dimensions of the Reich. Yeah, and it was important in a way to improve the flexibility of the network paths. Then we use, of course, a complex loss function that I'm not going to like go into detail, but it's available in the like the paper that we use. But it like of course had several loss terms with respect to the PDEs and initial and boundary conditions of the system for both matrix and fracture and their interactions, and other like loss terms. The training methodology that we used here was also kind of important for us because of the high the complexity of the optimization process. The optimization process easily failed into the spectral bias in a way, and diverged, and we couldn't capture the high frequencies of the system if we directly went to the most complex optimization process. So here we performed the multi-stage optimization that after initialization of the network properties or network parameters, we went to a pre-training stage that we kind of decoupled the matrix and fracture networks and let them to learn the characteristics of the flow independently without having any interactions. The reason that we applied this technique was that matrix and fracture had very different frequencies in the system. So the fracture quickly got saturated by water, while the permeability in matrix was very low. So it took a long time for it to gain some saturations. So here their frequencies was not very similar, and we couldn't train them at each other at the beginning of the process. So at the beginning we decoupled them for the training, but we needed fractures for matrix. So we applied a simplified strategy for showing the impact of fracture. We here use the Buckley-Leverett fracture modeling strategy that assume that fractures are one D behavior using a very this Buckley-Leverett method, and calculated the properties of the fracture or the saturation of the fracture and pressure of the fracture at each time using Buckley-Leverett technique. And so then we had some information about the saturation of fracture at each time using a very simplified process. And then we use those saturations as the boundary conditions or Dirichlet boundary conditions of the matrix. So we defined fracture as some constant, some boundary conditions in the system that was saturated by water, and it led the fracture it let the water to imbibe to the fracture to the matrix, very using fully imbibition flowing method. So it was only driven by capillary forces. So using this technique, we could apply both impact of fracture in matrix and train the fracture network independently. This assumption was critical for us to pre-train the network, but the assumption was more or less valid for systems that we have very high contrast between the properties of matrix and fracture, because the fracture quickly got saturated by water or by wetting phase, and it's not very important how you model it because it's getting very much saturated by fracture, by the wetting phase, I mean. then we moved to the fully coupled training, and during this fully coupled training, we calculated the interaction terms between matrix and fracture based on the properties of the calculated properties of the matrix and fracture networks. So it was a kind of fully coupled training and allowed the dynamics of the interaction between matrix and fractures easily. But here, because we had a very different kind of frequencies in matrix and fracture, we needed to go with a lower learning rate to avoid the optimizer to fail in a way. And of course, we could increase the number of collocation points to have a higher training with higher accuracy. We use adaptive loss terms to avoid the errors at high error zones. That helps us to increase the flexibility of the network and avoiding falling into this divergence of the optimizer. And of course, we perform resampling of collocation points at each time. That helped us to use lower collocation points for the training instead of using all the collocation points that we have. We use random initialization of the time at each at some periods of training, and change the collocation points that we are training based on that. So we kind of resample the collocation points at each 10 epochs. And it helped us to reach to a uniform distribution of errors at each at the total domain that we had, but going with very lower number of collocation points and reducing the training time. So this is the collocation points that we had. This is the PDE collocation points for the boundary conditions at inlet and outlet. At radial area that is blocked, so it's not, we don't have any flow here, and it should be considered during the calculations. And of course, the fracture collocation points, and we had also some collocation points with the matrix, for the matrix. Also, we had some experimental data. We had some information about the some low fidelity data about the recovery factor or the volume of the rock that is saturated by water, that can be calculated using both CT scan images and using some measurement tools at the laboratory. And of course, we had some information about the injected volume. And we had information about the pressure at two sides of the rock, at the inlet and outlet. And the injection was based on the constant pressure drop. So the pressures at each side were kept constant during the optimization. And of course, we had the CT scan images, high fidelity data. And this is the points that we had in a way. In total, we had about 1 million points, measured points, that measured using that 12 snapshots during the experiment. So we had dynamic imaging of the experiment, and we could perform calculations using those images. So before going to the real experimental data, we went to a simpler case that is a benchmark problem. And in this problem, we still had a cylindrical core and a vertical fracture in the middle of the rock, and then perform calculations. So here the calculations should have been much easier. So we wanted to see how our method is working and how it perform some sensitivity analysis on the different parameters and different meta parameters of the system. So this is the characteristics of the networks that we used. For the matrix domain, we used a network with 8 like latent layers, and each layer with 18 neurons. Like for fracture, we use 6 layers and 60 neurons, and we use the Adam optimizer. We couldn't go to this LB-FGS, like it failed easily, and like I think it's understandable because LB-FGS is very sensitive to the scale of the problem, and yeah, for this problem, for this complex problem, we couldn't use it. Even with like a low learning rate and the batch size of 36,000 points. But of course we changed it during the optimization process. So like the number were constant, but the points that we had was like different at each stage. And the sampling process was random. So it wasn't based on any like any special time or a special like part of the core. So this is like the results of the calculations for this problem. And you can see that here we inject like water from one side and produce from the other side, but water bypasses the matrix and goes through the fracture, but then from fracture we have some flow to the matrix. So it's like a complex process. And like this is the comparison of results of pins and finite difference that we had. So we had access to a finite difference simulator for this process. And you can see the absolute errors for both the saturation distribution and pressures. And a snapshot of like the saturation distribution for both pins and finite difference. And you can see that like pins could with a good accuracy regenerate the like true data or true results compared to the finite difference simulator. Then we went to like performing inverse calculations. So for inverse calculations, we had access to the pressure, pressure drop in the system, pressure at each sides of the core, and the average saturation of water through time. So we didn't use in situ data for this problem. So the optimization was a bit much more complex in a way. And this is the results of the calculations for the system. So here we also went to a ensemble-based history matching. So we performed different initializations for the parameters of the inverse parameters, and performed inverse calculations several times. So we wanted to see like how much the results are sensitive to the calculated properties, to the assumed properties at the beginning. So it helped us to gain some information about like how much the inverse calculated properties are unique or not unique. So this is the result. So this gray distribution shows the distribution of the initially assumed or the initial values of rel perm and PC properties, and you can see that we had a very high distribution of the properties. And the blue curve showing the true curves, and the green and these purple curves is showing the distribution of the final properties of the system, the calculated properties in a way. So we kind of got very interesting results here. So at first we were looking for relative permeability curves and the capillary pressure curves. You can see here that the calculated properties for matrix for relative permeability and capillary pressure curves at the end was not at all similar to the true properties of the system or the true capillary pressure and relative permeability curves. And it was very interesting. That's why we couldn't recover the true parameters. And you can see that the distribution of errors for this case was very high. But from before, we knew that when we have imbibition as the main governing mechanism in the system, in our previous papers we proved it. Here, because the main mechanism was imbibition mechanism from matrix to the fracture to the matrix. So here we didn't have any very significant viscous flow, but the most mechanism of the flow was driven by imbibition or by capillary forces. But when we have capillary forces, we cannot get a unique solution for the capillary pressure and relative permeability curves, because we have thousands of or infinite number of relative permeability combination of rel-perm or relative permeability curves and PC curves that can lead us to the observations that we had. But a specific kind of combination of these curves that gives us the capillary diffusion coefficient, we call it, or it's kind of diffusion coefficient in the system. So if we calculate this capillary diffusion coefficient or lambda, then we will have a unique result or unique calculated curve. And we again obtained these results here. So we can see that although the calculated properties for relative permeability and capillary pressure are very, very different, and of course they are not even close to the true curves, but the CDC curve, that is a combination of these curves, is very close or kind of matched with the true curve, and it showing very low errors. So this was an interesting part of the results that we had that was very interesting for us. Yes.
Yeah,
so
I have actually a question.
yes.
That how viscosity can change this result. I mean, you said in this case the viscosity was not too much, but if it was, then how can a result change? Because I think increasing viscosity will make those partial differential equation more stiff.
Exactly. Yeah. Here because we didn't have the pressure was very high, so we had about 40 bars of pressure. So in 40 bars, water is incompressible in a way and don't have too much change in viscosity. And CO2 also is kind of behaving like an incompressible fluid and with very low changes in viscosity. So here we assume the viscosity of system to be constant. But if complexity increases, if viscosity increases or changes through the time, of course the complexity and the stiffness of the system increases. Yeah, so in that case, maybe the evaluations would be different, but here the properties that we are calculating are kind of the natural properties of the rock in a way, not the fluid. So the fluid is not the fluid properties are not included in a way here. Of course, viscosity of fluids are impacting the CDC curve itself, but the value itself is can be independent of the system in a way. Yes. Then we went to the real experimental data. So this is the CT scan images that we have. This is the fracture in the core, and this is showing that how the saturation is distributed around the fracture. So from fracture to the matrix, we have some flow that leads to production of CO2 from the core, from the rock. And this is the showing how this flow is occurring. And this is the cylindrical rock that we have in a way. And this is the dimensions of the network that we use here, same as before. And for inverse calculations, here we have P's results, we have finite difference results, and we have experimental data. So for inverse calculations here, again, we used only recovery factor and injection volume and the pressure distribution in the rock, or pressure drop in a way, not distribution, and performed inverse calculations. And then the inverse calculated properties was used to performing simulations using finite difference. So before that, we didn't have any information about the properties of the system. So we calculated it using pins, then used those properties to perform finite difference simulations. And here you can see like the simulation results. Like, of course, numerical simulation is showing much like better distribution of the system, more better physically in a way. But both of them are showing good results in a way. And like they're kind of very close to the experimental data that we have. But consider that here we didn't use the experimental data for the training or for the inverse calculation. So only using by having the fracture and by having kind of some experimental observations, we could guess the distribution of fluids in the Reich in a good with a good accuracy in a way. That was like very interesting. Then we used those data here like for performing the calculations. Here the like the inverse calculated properties. Here we don't have any information about the true curves, obviously. So, but we use the calculated curves for like resimulation of the system using finite difference simulation, forward simulation, and you can see that using the forward simulation, using a numerical simulator, we could get exact recovery curve. So it's showing that the calculated curves is accurate in a way, and it's showing the exact properties of the system in a way, or the properties of the system on average. And also we calculated the properties of the fracture here by matching the fracture, the produced and the injected volume. Here we can see that, so we calculated to see that how much of the flow is occurring in fracture and in matrix, and you can see that about like 99% of the flow is occurring through the fracture, so it's passing through fracture because fracture is having a very high permeability, and like less than 1% of the whole flow or the velocity is like occurring through the matrix. So here, so it's showing that the most of the injected fluid is passing to the fracture and like produced to the other side very quickly. And using that, we could calculate the properties of the fracture or permeability of the fracture. So here we calculated both properties of matrix and fracture at the same time. Like that, like was not very easy to be done like using the other techniques or numerical techniques. Here we didn't have like a prestigious and very well developed inverse calculation tool for comparing pins with the like a reference reference inverse calculations toolbox. But here we used like a optimizer, Nilder-Mid optimizer, coupled with a finite difference simulator that we have to compare the results with pins, with the results of pins for inverse calculations. And you can see that how much is pins inverse calculations are quicker compared to like finite difference simulation, because like we saw that like performing like one inverse calculation using pins is kind of similar to performing one forward calculation using finite difference simulator in a way, like with some levels of course, difference and errors. And yeah, so it shows that like pins simulator is much quicker than the finite difference simulator for inverse calculation. That is like very important for us and saves lots of times. But also, like even finite difference simulator couldn't perform very well in this system because of high gradient of the like properties between matrix and fracture. It easily diverged, and it like led to like very low simulation time or time steps that like made the reaching to the final results or final time of the simulation almost impossible for some cases with very high gradients. So here we can see that pins was much better than the finite difference simulator that we compared. And like this is like analysis that we show that how much it's important to consider the impact of fracture to like and the accuracy of the inverse calculated properties. Like because in many cases in industry, like engineers, like because they want to get the results much quicker, they try to avoid the impact of fracture or overlook the fractures. Either they choose some like racks without any fractures, or they like neglect it. And there are many, in many times, like the cores are actually fractured, but the fractures impacts are overlooked in a way. So here we neglected the impact of fracture and performed the inverse calculations, and we saw that how like orders of magnitude difference in the properties of the matrix, in the calculated properties of the matrix, that like shows that how it is important to go with the very like high fidelity simulations with like coupled matrix and fractures, not overlooking the impact of fractures that is like a normal in industry at least these days. And of course, later we used those in situ data or high fidelity data for performing calculations, and like removed the recovery factor data and just used the in situ high fidelity data with like 1 million observations that we had through the time of the experiment. And here we performed two evaluations. One, like we have, so this is the experimental data that we have. This is the true experimental data with lots of noises through the CT scan images. Here we performed some krigings to like remove these noises, like to help pins to perform inverse calculations and like remove the noises that it has. And we compared the results of two cases, and so that so like actually pins didn't need any like kriging in a way for the experimental data, and it could easily like remove the impact of noises that we have in the observations. And of course, the calculated properties, the CDC curve or the capillary diffusion curve for both cases were very similar to the calculations that we had before in the previous stage. That shows like it was accurate in a way. And using like a technique, we also performed some uncertainty analysis on the properties of the fractures or on the distribution of fractures by regulating the discrepancy between the images that we had and the pins and the initial assumed fracture distributions. And using here, we could like gain some information that at which zones like the considered fractures are a bit uncertain based on the images that we have. And you can see that in red areas we have high uncertainties in a way, but in blue and in gray areas we don't have too much uncertainties, and in blue areas we have some level of uncertainty. So it like helped us to gain some information about discrepancies between the assumed state of the system or boundary conditions of the system and the data that we had. So key conclusions here is that so pins can be used for performing forward but mostly inverse calculations in capturing like multi-scale fluid dynamics, and it can capture noisy data and like give us some good information about the system very quickly compared to the rival methods. That like it's very helpful for many cases in industry and in like academia that can be used later in many fields, and of course in the field of modeling flow in porous media. But it's good to like point some challenges that we had. First, first, so we saw that moving to more complex network, fracture network distributions or complexity of the optimization process, the optimizer performed weaker and weaker in a way. So kind of we think if we had more complex fractures, like we even will need more advanced training strategies or network architecture or network sizes. But of course, with increasing the network size and the total size of the network, the computational time increases, and the network will fall into this spectral bias and other biases in a much easier way. So we have some kind of problem with both increasing and decreasing the size of networks here in complex processes that should be considered in the future studies. The optimization process was very unstable because of the very highly complex loss landscape of the system, and it could easily fall into a spectral bias. So a spectral bias here means that we couldn't capture the impact of fractures in the matrix, and fractures could be easily bypassed in a way in the calculations. So for forward calculations, it was very time consuming, but of course effective for inverse problems, for inverse calculations. And the other important problem, challenge was that we had lots of tunable hyper parameters. So still there are some challenges for getting some reliable toolbox that to be used for in realistic cases by non-technical people or non-technical in this field easily. So it still needs lots of trial and error to find some good predictions from the system and good results in a way that should be solved, of course, in the future for realistic applications. Yeah, thank you so much.
Thank you, Jassem, for a very informative talk. So I'd like to request the participants, if you have any questions, to unmute yourself and ask if you have any questions at this point. So I think it's so can I quickly ask you a question on the pre-training that you were discussing in one of the beginning slides? So if my understanding is correct, you were solving 4 sets of PDEs, so representing the wet and the non-wetting phases for both the metrics and the fracture, right? So when you have a pre-training that you're doing, which you told that you're doing independently, so how do you account for that, the interaction terms, basically that the Q parameter, I believe, which is what mimics that behavior of, transferring the information from metrics medium to the fracture medium, right? So when you're doing it independently, how exactly are you accounting for that Q parameter? Is it you're feeding the data that is already known to you? I'm kind of curious to know that.
Yeah, thank you for your nice question. So Q parameter that you mentioned, is impacting both matrix and fracture in a way. But for the fracture system, it's nothing. It's easily negligible because most of the flow is occurring through the fracture itself, not going to the matrix. But for matrix, it's important.
Yeah.
Because main source of flow in matrix is from the fractures.
Right.
So here we easily neglected the impact of that Q in fracture during the pre-training. But in matrix, we assume the Dirichlet boundary condition. So we solved this. We used the Buckley-Leverett equation to calculate the distribution of saturation through the time in fractures, and we assume fracture a 1D system. We neglected the dimensions of the fracture in a way, because the most of the pressure distribution is along the core here.
Right.
not at other like dimensions. So this Buckley-Leverett theorem can be easily like applied in a way to have some clue about the saturation distribution versus time in the fractures. When we have saturation distribution in the rock in the fracture, so we can use those saturations as the boundary conditions in the matrix at those points at the interactions in a way. So it behaves like a fracture. It's like imbibition phase.
Right.
So it seems like we don't have any pressure distribution between matrix and fracture at their intersections, but
Right.
we have some capillary forces that like kind of pushes the water to the matrix. So and that's actually the main governing mechanism in this system. So this system is mainly governed by inhibition. So using this assumption, we can easily like have some very high like percentage of the true physics in the system during a pre-training. So the impact of matrix and fracture can be easily captured in a way. So when we go to the fully coupled training process, already the impact of fracture are considered. So we start with some level of pre-trained system. So we just need to fine-tune the system at the fully coupled stage. Most of the
Right.
calculations are already done in the pre-training.
Right. And also like so I think it clears my question to a good level. So another other thing is like the QI that you mentioned, it's something that is only applied on the surface, if I'm not wrong. So it's basically occurring at the surface of the matrix and the fracture. So once you move away from the surface, you don't need to consider QI. So it's fine to say.
No, there is no interaction between them. So they're only that their intersection they have the
So,
interaction.
so why I asked the question was because from my understanding, the QI had to be complementary. So when you have positive QI on matrix, it should be negative QI on the fracture. So that's why I wanted to like I was kind of curious to know how you were able to do it independently when you had such dependencies. But thank you for that information. Thank you.
Thank you. Yeah. So it's like the other the points that we don't have an intersection. There is no Q at all. So
Right.
yeah. Thank you.
But otherwise, I think it's pretty much like I think I don't see any questions on the chat box, so I think we are pretty much.
I actually do have a question.
Okay,
if you don't
sorry.
mind.
Yeah, please go on, Corey.
Yes, and thanks again for extending the invitation, Professor Jagtap. Let's see here. Great talk. My question to you. Unfortunately, I was a couple of minutes late to your discussion. Could you potentially go back a few charts to the mathematical model? I think I missed something, and I just wanted to just understand.
Here?
The physical model. Yeah. You are capturing like surface energy in somewhere here, or for like the so you've got a porous media, right? Are you assuming, and it's really maybe two parts. One question is, when you're talking about a fracture, right? This is basically where you have a void, correct? Right? So a non-wetted area in here.
Yeah. Yes. So fracture, like in theory, and like in the very very ideal system, it's not a fractured domain. So it's a very void area and it's like solid and very rigid. But in practice, like there are always some particles in fracture. So it's kind of, we can call it some high porosity and high permeability and low permeability porous media in a way in practice.
Oh, I see. Okay. Are you assuming that everywhere in the blue region, this porous media has like, let's say, uniform, like a uniform distribution, like so like in a porous model, like you could like let's say like the packed bed model, right, where you assume like it's all uniform spheres, like in a lattice type of thing. Is it that type of arrangement that is what's in the blue zone that is wetted, or you have these two fluids mixing?
Yeah, so here, like we assume the matrix, matrix at its domain is homogeneous, and fracture at its domain is also homogeneous. So properties at like each part of the matrix is same. That is like not very far from reality. So we had information about the porosity distribution, and it was like it was very homogeneous in this system. So, but here like we perform that assumption, but it can be, of course, easily that assumption can be easily like expanded to a more general system of like kind of heterogeneous porosity or permeability, even if you have information. Yeah, but here we assume it very homogeneous system.
And so back to my, and again, thank you for clearing that up. I was something I wanted to understand. And the other thing as well, when it comes to the setting of the interaction between CO2 is in the gas phase you mentioned before, right? You have CO2, liquid water, and CO2 gas. Was that the two phases coming together? Okay. And so like I'm actually studying capillary flow. I'm using CFD methods though, and you could say it's a similar thing. I'm looking at capillary flow in woven screens, right, which is kind of akin to this problem, right? It's you have a you could think about it as if like it's a void, or you have a wetted area that in the fracture you could say is where the wires would be of these woven screens. So I'm looking at air and water. So do you set anywhere like one thing is the static contact angle of like between the solid, gas, and liquid phases? Could you, and again, I probably missed it, where that's captured here? Is that in Darcy?
Yeah, so here so capillary pressure impacts is like defined as the pressure difference between the two phases. So pressure.
Okay.
Yeah.
I think. All right.
So
there
we
it
have
is.
PC, the capillary pressure, and
There's surface tension right there.
tension,
Okay.
and yeah.
Perfect. Yeah. Okay. I'm sorry. I
No.
missed that part of it.
Thank you for asking. Yeah. So that's a very important property of the system that we are looking here because of these imbibition and capillary forces. Because here the capillary forces are the main flowing mechanism in a way.
Right. Okay. So at every. All right. Yep. I didn't spend enough time looking at this chart. Thank you. That's perfect.
Yeah. Thank you so much.
Do you have a paper also on this work?
Yeah. Paper is online. Yeah. So this is this archive number and with the title, of course, the title.
Thank
you very much.
Paper.
I'm sorry, Professor.
I'll send you the paper link.
Okay. Thanks very much. Thank you.
Thank you.
Okay, so if there are no questions, I would like to thanks Jassem. Thanks for your time and the wonderful talk.
Thank you so much for inviting me, and it was my pleasure. I enjoyed.